Take a look at the diagram on the front board here, the picture that you see of this blue with some white lines there. Tell me what it is that you see. Sorry? Scottish flag. Yeah, close. Close. It's kind of maybe a drunken person painting a Scottish flag, maybe, but yeah. No, it's not the breaking of the sound barrier, no. It's just airplane exhaust. It's condensation trail behind airplanes. We call it a contrail sometimes. Condensation trail or a contrail behind airplanes. Okay, tell me what you know about these airplanes. They're probably going fast, yeah. They're probably going pretty fast. Otherwise, they probably wouldn't be flying if they were going slow, right? What else do you know about these did you say airplanes? Yeah, okay, so there's two of them, right? There's two airplanes. What else do you know about these airplanes? How do you know they're traveling at different speeds? Okay, the size of the condensation trail. Okay, I'm not sure that tells us they're traveling at different speeds. We see this one is quite a bit wider than this one. Not sure that tells us about the speed, but rather different times. Yeah, I would say, Holly, is that what you're going to say? Yeah, which one was closer? Like which one was further back in time? Which one was closer in time? We'll call them 1 and 2. Which one was most recent? 1, yeah. 1 is going to be the most recent. Number 1 is the most recent, and we know that because these condensation trails haven't spread out as much. Okay. Over time, it spreads out and kind of gets a little bit more fluffy, a little bit more cloud-like, right? Which is really what it is, right? It's a cloud. It's a condensation trail or a cloud trail behind these two airplanes. Okay, 1 is the most recent, 2 is a little bit further back in time. What else do we know? There's 2 planes. Number 1 flew by recently. Number 2 flew by, well, recent enough that we can still see the condensation trail, but further back in time. What else? 1 seems like it was higher. Which one seems like it was higher? Number 1 seems like it was higher? Because they're narrower lines? Okay. It does actually look like it's a little bit behind the fog there. So we'll say number 1 is higher. Okay. What else? They're both what? Okay. You can really tell that with contrail number 1, right? With contrail number 2, you can kind of see that in here that there's 2 engines, 2 condensation trails, but it's a lot easier to see in number 1, obviously. Dan? Good, they're going in different directions. Can you tell me which way number 1 is going? Which way number 1 is traveling? Somebody said southeast, down and to the right, right? Whatever direction that is. And this one's going this way. You can tell that because as time goes by, it kind of spreads out a little bit. And you can see in this one that it's clearly spread out more here than it is here. Therefore, it's coming from here to here. This one's going from here to here. So just by looking at this picture, I didn't mention to anybody what this was. I just said, tell me what you know about this picture. Somebody told me that it was 2 airplanes. Somebody told me that the first airplane flew by most recently. Somebody told me that number 1 looked to be higher up. Somebody told me that there was 2 engines in each of the airplanes. Somebody told me the direction they were going. One other thing we can tell, they didn't hit each other. They didn't collide. The condensation trail wouldn't look like this X, like the Scottish flag if they had collided, right? You just told me a whole bunch of things about these airplanes when I didn't even tell you that there was airplanes. You haven't seen the airplanes. I haven't told you that there's airplanes, but yet you gave me a whole bunch of properties of those airplanes without any knowledge other than the picture of the contrail that followed them. Now, how does this relate to what we do in Physics 30? We want to know, we've always wanted to know things. Okay, since 1897, when the electron was discovered, since 1897, when we first determined that there are things smaller than atoms, we've wanted to find out what was inside those atoms. It didn't take us all that long after Thomson and his cathode tube experiment to know that the atom consists of protons, neutrons, and electrons. But the next logical question is, what are they made out of? What are protons, neutrons, and electrons made out of? As it turns out, electrons aren't made of anything. Electrons are as small as it gets, at least we think they are. But protons and neutrons can be broken down into smaller things. They're not fundamental particles. They're made up of smaller things. But how do we know that? Well, we use things that we call particle accelerators and colliders. A particle accelerator accelerates, say, a proton to an incredibly high speed, sometimes as high as 99.99% the speed of light. Unbelievably high speeds. And then, in the ultimate Guy's machine, we smash them together. You want to know what's inside these things? These tiny little protons? Let's spend $1 billion. Let's get these things going as fast as we possibly can. And then let's have a head-on collision between the two. And let's smash them apart. And let's just look at what's inside. Isn't that such a Guy thing to do? We're curious. Men and women are curious. Men and women want to know what's inside here, what's inside these protons. The best way we have to do that is to accelerate these charged particles, these protons, to incredibly high speeds and then smash them together. Now, we have to have really, really high speeds because we want to overcome the strong nuclear force that exists within the nucleus, exists in the atom and exists in the nucleus. Strong nuclear force, remember, is a force that pulls things together in the nucleus. We have to overcome that if we want to break it apart. Right? We've got to beat that. Okay, it's like you got two cars. They collide at 7 kilometers per hour. We don't overcome the forces that hold that car together. The cars don't disintegrate. They might get dented, but the cars still look like the cars. If they collide at 150 kilometers per hour head on, then the cars disintegrate, and we find out what's inside those cars. We have to have big speeds and big energies to overcome the forces inside, to overcome the strong nuclear force and the weak nuclear force within these particles. Once we do that, once we've accelerated them to great speeds, once we've smashed them together, once we've broken them apart, we've got to have a way to observe what came out of it. These particles are way too small to be seen with the human eye, so we've got to have a way to observe it. There's a couple of ways, a couple traditional ways that we use to observe them. One's called the cloud chamber. The cloud chamber consists of this area, this chamber, that has a dust-free mixture of air supersaturated with either water or alcohol. So it's basically ready to rain water or alcohol. Okay, just about to that point where it's going to rain water or alcohol. Now these charged particles that come from the smashed up protons, in other words, the little things that make up the protons, they ionize molecules. They ionize the water and the alcohol molecules. These ionized molecules cause the vapor, cause this gas to condense. We form a condensation trail behind these particles. These charged particles that come from the smashed up protons. So you smash these protons together, you get a bunch of little things come out of it. These little things ionize molecules, and these ionized molecules in turn cause a condensation trail. So indirectly, we're going to observe these tiny little particles that came from the smashed up protons, these subatomic particles, simply by observing the condensation trail that follows them. Just like we observe the condensation trail that follows the airplane. We observe that contrail, we're able to determine a number of properties of the airplanes without ever having physically seen the airplanes. Here, we're able to determine a number of properties of these particles that come from the smashed up protons, these subatomic particles, without having ever seen the particles. Now, another way we can do this is with the bubble chamber. Bubble chamber works similar to, but yet almost opposite to, the cloud chamber. Here, instead of having this dust-free air that's supersaturated with water and alcohol, in other words, instead of having a vapor, what we have here is a gas that's been liquefied. So it's the exact opposite, right? Instead of having a gas, we have a liquid. It's at a low pressure, which lowers its boiling point to a value that's just barely above the temperature that we're actually at. So in other words, it's just getting ready to boil. It's almost ready to boil, but it's not quite boiling yet. Now these charged particles that come from the smashed up proton, the things that make up the proton, they cause ionization again. These ionized molecules, instead of causing the gas to turn into a liquid, they cause the liquid to turn into a gas. Instead of following the condensation trail that we get right here, the cloud trail, we follow the bubble trail right here. So we never see these things that make up the protons or whatever particles, but we can see the trail they leave behind, which doesn't tell us everything, but tells us a whole lot about what produced the trail, just like the contrail following the airplane told us about the airplanes. This is a photograph of a condensation trail. You might see something that looks like this. You get lines going everywhere. Some of them are straight, some of them are curved, some of them are circular, some of them are spiraling. What do we learn from this? It's pretty hard to interpret that just by looking at it without knowing what went into this. Now, what probably caused these to go in circles was maybe a magnetic field that was introduced. We introduce a magnetic field in here. We look at which way these particles bend as a result of that magnetic field, and we can determine what kind of particle they are, positive or negative. We introduce an electric field. Maybe we introduce an electric field and a magnetic field together. Maybe we can cause some of these particles that we're bending in the magnetic field to now go in a straight line. From that, we can determine the speed and the energy of these particles. By observing this condensation trail and introducing some outside factors like electric and magnetic fields, we can determine a lot about these particles that make up the protons. All right, what are the particles that make up the protons? Everything that I write in black here is important, but it's more for perspective. If I write it in red, it's something that you have to know. Not for tomorrow's test, but for the final exam coming up in a couple weeks. We have two types of particles, two types of particles that basically any particle can be broken down into. There's the fermions and the bosons. Remember, this is in black, so you don't have to remember these terms, the fermions and bosons. I can't just give you the ones that you are expected to memorize because it won't mean anything to you. Okay, it doesn't make sense to me to tell you about just a handful of particles if you don't have the perspective of where they fit in the puzzle. So I'm going to show you the puzzle and then just ask you to remember the pieces of the puzzle. But I still want you to have that perspective. The bosons are particles that mediate forces. In other words, that cause forces. What causes an electric force? What causes a magnetic force? Well, say, like, okay, two magnets cause a magnetic force. Yeah, but why? They're not touching each other. What causes this magnet to be attracted to this magnet? Bosons. Okay, bosons mediate forces. The fermions are the particles that interact because of the transfer of bosons. So the bosons are these particles that allow fermions to interact with each other. Now, there's two types of fermions that we're going to talk about. Those are the ones that we really need to worry about, the fermions. There's the leptons, and there's the hadrons. The leptons are particles that are not affected by or not mediated by the strong nuclear force. In other words, that force that acts in the nucleus has no effect on these leptons. These leptons, as far as we know, are fundamental particles. They can't be broken down any further. An example of a lepton would be an electron. As far as we know right now, an electron is as small as it gets. Kind of going along with the electron would be the electron neutrino. You guys learned when we talked about beta decay, beta minus decay, and beta plus decay. A neutrino is produced. Well, that neutrino that's produced is an electron neutrino. It's what we're talking about right here now. We just didn't call it an electron neutrino at the time. We just called it a neutrino. We also have some other types of leptons. We have the tau. And we have the tau neutrino. We have the muon. And we have the muon neutrino. So 3 different types of neutrinos. The one we've always talked about and the one that we'll always will talk about is the electron neutrino. Since we're only talking about the one, we often just drop that word electron and call it a neutrino. But understand that there are 3 different kinds. In addition to these 3 types of leptons and their neutrinos, we also have the antiparticles. The antiparticle of an electron is positron. The antiparticle of a neutrino is an antineutrino, an electron antineutrino, an anti-tau, an anti-tau neutrino, an anti-muon, an anti-muon neutrino. We need to be familiar with the electron and the electron neutrino, the positron, and the anti-electron neutrino. Now, the hadrons, they're not fundamental particles. They can be broken down into smaller particles. An example of a hadron, by the way, might be a proton. Or a neutron. They're made up of quarks. Ever heard that term, quarks? If you have, you may have kind of heard it loosely described as something that makes up subatomic particles. Something that subatomic particles could be broken down into. Well, it's partly true. Protons and neutrons can be broken down into quarks. Electrons can't, because the electrons are leptons, and they're as small as it gets. But the protons and neutrons can be broken down into quarks. There are 6 types of quarks, 2 of which we need to know. Whoops, that's not the one I want. There's the up quark, and there's the down quark. There's also the top quark and the bottom quark. There's also, and this is the weird one, the charm quark and the strange quark. To give you an idea as to how we're still developing this model, when I was in high school, and I mean, I know that was a long time ago, 20 years ago, 23, 24 years ago. When I was in high school, they hadn't found the top quark. The top quark was this mysterious thing that scientists thought existed, but nobody had ever found it. Okay, now we know, now we've seen the top quark. We know that it exists. The up quark and the bottom quark are the ones that we need to know. In addition, there's the antiparticles. So the anti-up quark, you'd think the anti-up quark would be a down quark, right? But it's not. There's the anti-up. There's the anti-down. There's the anti-top, the anti-bottom, the anti-charm, the anti-strange. We just don't need to know the last 4. Now, the charge on an up quark, and this is on your data sheet, so you don't need to memorize this. The charge on the up quark is 2/3 plus 2/3 of the elementary charge. The charge on the down quark is negative 1/3 of the elementary charge. And of course, the charge on the anti-up would be negative 2/3, and the anti-down would be positive 1/3. But again, those charges are on your data sheet. You don't need to memorize those. So far, so good? A lot of stuff on that page, but you can see that there's not a ton that we need to remember. Right? We need to remember what's in red. The black stuff is perspective. Finally, the last page. This is where it all ends. We're going to revisit beta decay just briefly and express beta decay in terms of the quarks that we've just learned about. This is an up quark, a down quark, and a down quark. Up, up, down. An up quark has a charge of 2/3 the elementary charge. A down quark is negative 1/3, and a down quark is negative 1/3. Those add up to give me a charge of what? 2/3, negative 1/3, negative 1/3. 0, right? The charge is 0. That means it's going to be a neutron. The only thing that has a charge of 0 is a neutron. Now we got up, up, down. We got 2/3, 2/3, and negative 1/3. What do those add up to give me? 2/3 plus 2/3 plus negative 1/3 is 3/3, or plus 1. Charge of plus 1. What's that going to be? Proton. When a neutron splits into a proton and an electron and an antineutrino, we call that beta negative decay. Take a look at the bottom one here. 2/3, 2/3, negative 1/3. Well, that's a proton again. We got 2/3, negative 1/3, negative 1/3. That's going to give me 0, which is a neutron. A proton changes into a neutron, and what's this? Positron in a neutrino. That's going to be beta plus decay. Now this thing right here, don't lose any sleep over that, okay? That's what we call a virtual particle. It's really kind of a two-step process in a sense. Proton changes into a neutron in this virtual particle. Then this virtual particle decays into a positron and a neutrino. As far as you're concerned, it's good enough to remember that a proton changes into a neutron, a positron, and a neutrino. And you can kind of consider it to be skipping this intermediate step if you want. It's, from the perspective of a Physics 30 student, it's okay to forget that virtual particle. Yep. Could be. Yeah. Yeah, that's entirely possible, yeah. The question, if you didn't hear that from Rob, was on a diploma exam, could we get a question where we have to name the type of decay it is, based on the quarks? And the answer is absolutely, it's possible. Now, having said that, I haven't actually seen that all that often, but there is actually a quark question on your test tomorrow. I've already photocopied it. I'm just not going to ask you to do that question. I can't remember, to be honest, whether it just asked you to, up, up, down. Is it a proton, neutron, or electron, or whether it asks you to identify something like this? I can't remember. But yeah, that is fair game. It doesn't appear all that often, but it is fair game. Well, it's on there to count as a bonus mark. So. We'll see. We'll see. We'll see. That's it. We're done.